Alrighty, welcome to another video. This is a continuation on lesson 14, which is involving rational equations. Here, we're going to have applications, which is going to be word problems. And again, not gonna lie, I think this is probably one of the tougher videos or tougher sets of problems of the entire course. I probably said that same for the last set of word problems and the system of equations stuff. It's just because word problems are tough, right? Not only do we have to interpret the word problem, but then we get an equation, then we have to do an equation thing, right? So what's the game plan? In general, the game plan, we interpret the question to try and create an equation for the word problem, and then we use the prior videos or the prior strategies we've learned, this last part of the course, to hopefully solve that equation we create once we create the right equation. And creating the equation is probably the hard part because you have to use logic to kind of interpret what's going on. So this one, I would say, is kind of more of a little bit of a warm up, right? It's just more just math related, right? If some number is added to both the numerator and the denominator of the fraction 3/4, the result is 3 greater than that number. So I see some number, so I don't know what that number is. What is the number? Okay, it's looking for what that number is, right? We can just call that number, I don't know, let's call it a variable. Let's call it x. And what do we do with x? We add both to the numerator and the denominator of the fraction. It's 3/4. So I have 3, not 3/3, 3/4. And you say we add both to the numerator and the denominator x. So that's what I'm going to do. That is what, if I was to highlight all of this, that is what this is. Cool. All right. The result's that will be equal to 3 greater than the number. Well, that number is still, I guess it looks green now because I double highlighted. That number is still x. So the result is 3 greater than the number. How do I write that? Well, I take my number and I have 3 greater than it. And there we go. The way I wrote this, I don't really care for 3 plus x. I'm going to change this to be x plus 3 over x plus 4 equals x plus 3. And you can ask, okay, what is the number? Well, let's solve for x. How do we solve for x for rational equations? Well, in a problem like this, you can cross multiply, right? So I'm going to cross multiply to get x plus 3 is equal to x plus 3 times x plus 4, right? Multiplying these together, and the cross multiplying 1 times x plus 3 stays the same. And in these problems, we have to set it kind of equal to 0, which means we need to expand it out, multiply, combine like terms, and then refactor. So it's a little bit annoying. I'll do the box method for us here. So we have x, 3, x, and 4, right? What is this? X squared, 4x, 3x, and 12. So I have x plus 3 is equal to x squared plus 7x plus 12. Let's subtract x and 3 from both sides to cancel everything here. So this is x squared. So 0 is equal to x squared plus 6x plus 9, it looks like. Cool. Are we done? Not yet. We're trying to find what the number is. We're just doing some setup so we can find the number, because then we can use the factor game. We have 9 on the top and 6 on the bottom. 1 multiplies at the top to become 9, adds to become 6. That's 3 and 3. So now we can factor to x plus 3, x plus 3. Zero product property means we can split this to 2 solutions. But when I subtract 3 from both sides, I get x is equal to -3 and x is equal to -3 here. So I get one solution. What is the number? What is the number? The number is 3. Okay, not the end of the world in terms of problem. This kind of required a lot of calculation, right? Maybe the interpretation part wasn't as tough, but this is one of the tougher kinds of rational equation problems. So, pause the video if you struggle in a spot and see what did I do in that spot and work from there. All right. So I have a little bit of space here. A kind of problem is what we call proportion problems. Proportion problems are like one of the more easier types of word problems because they deal with proportions, or in particular, they deal with equations that look like one fraction is equal to another fraction, right? Here, let's maybe stop like that. So if you have an equation where one fraction is equal to another fraction, and say this, we have like number, 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 and x, you can do, again, cross-multiplying stuff to figure out what the value is. And normally the proportions are kind of in certain units for the numerator and the denominator. So let's just look at like this example. A machine produces 312 volts in 30 minutes. At the same rate, how many minutes does it take to produce 260 volts? So if I was to create a proportion, I can have a fraction. Proportions and fractions are kind of like synonyms here. I can have the fraction of volts per minute. Another example of this we've often seen, maybe in like real life, would be like miles per hour. When you're driving a car, I would do, excuse me, I would do miles per hour, right? So I went, 30 miles in 2 hours. That's how I would say, how many miles per hour? That's 15 miles per hour, right? That's how you would do it for miles per hour. Volts per minute. Well, what do we have in this one? Well, this is saying 312 volts in 30 minutes. At the same rate, if we're continuing this same rate, if it's an equal rate, how many minutes would it take to produce 260 volts? Well, I don't know how many minutes. I do know how many volts. So I'd be 260 volts per how many minutes? I don't know. Let's put an X. All right, now we do cross multiplying. If I do the cross multiplying, I have 312x is equal to that. So 312x is equal to, 260 times 30. Oh man, I don't know that off the top of my head. Let me bring this out. 260 times 30 is 7,800. 7,800 here. Well, how do we get x by itself? Well, let's divide by 312. Divide by 312. That means x is equal to what? What is x equal to? I should have kept this up. What is it? Let me put it here. 7800 divided by 312 is 25. So that means, I guess, let's go in the context of the problem, right? How many minutes would it take to produce 260 volts? It takes 25 minutes. Like so. Not bad. Okay, another proportion problem for us here. The residents of a city voted on whether to raise property taxes. The ratio of yes votes to no votes was 5-3. If there were that many total votes, how many yes votes are there? Okay, well, I see a ratio of yes to no is 5-3. So let's try that out. Let's go. I can have a yes vote to no vote, and that would be a 5-3. 5 yes votes per every 3 no votes. Just like 312 volts per every 30 minutes, I can do the same problem here. Here's where things get like a little, man, this is weird. Um, if there were a total of, I don't have any yes votes or no votes here. I have a total amount. So I can't put 7952 on the top and put X like that because that's not yes votes, that's total votes. Similarly, I can't put this on the bottom either because this number is not representing no votes. So it would be nice if instead I had one of these be a total votes here. And we're looking for yes notes. So let's make this instead yes per total. Well, this gives us a yes per total. If I have 5-3 for yes to no, then if I had 5 votes for every 8 votes in total is going to be yes. So total votes in this ratio is 8, right? Because there's 5 yes and 3 no adds up to 8. Okay? If there were 7,952 votes total. So 7,952 total. How many yes votes were there? That's how I would say how many yes votes. Well, I don't know how many. Let's put it as an X for us here. So again, we cross multiply, makes life a little easier for us. I have what? Again, we're going to start using calculators here, right? Because I don't know. I don't know what 5 times 7,952 is. That's 3,9,760 is equal to 8x. And then we can divide by 8 to get divided by 8. X is equal to 4,970. All right. Now, back to this problem. What was my X here? We had this many total votes. How many were yes votes? This 4,970. So this many yes votes. Well, maybe the question would have asked, how many no votes are there? Or you can find out how, if there are this many total votes and these ones were yes votes, how many no votes are there? Just subtract, right? Not that bad. Okay, in my opinion, these problems start to get like way, way rougher here. So let's kind of like, just work at it. Sorry, this might be even longer video too. So here now we're going back to distance equals rate times time problem. So maybe we've kind of done some of this stuff before. I kind of did an example earlier. Um, we have rates, we have time, and what would be like a distance. Well, say you're like a runner, say you're in cross country or something like that, and we want to run 5 miles per hour or something like that. So we're just doing like a brisk jog, right? If I run that amount for 3 hours, right? Going 5 miles an hour for 3 hours, my rate is 5, my time is 3. Well, what's my distance? Distance is 15 miles. Now, if you can run 15 miles, kudos to you. I would not be able to do that. But that's how the process would work. It would take 3 hours of running. Yikes, right? Whenever we do distance equals rate times time, I like to do d equals r times t, like that. But sometimes, sometimes the problem doesn't give you r, or sometimes the problem doesn't give you t. So we can, using this prior rational equation stuff where like, oh, let's solve for a different variable. If I started with d equals r times t again, I could have divided by r on both sides. And I'm left with an equation for time. Time is equal to distance divided by r. That's kind of cool. Or again, if I started with distance equals rate times time, I could have divided by t on both sides. And now I have r by itself. I've solved for r, and r is equal to distance divided by time. And that's actually like, again, when I've said miles per hour, that's like the rate of miles per hour. Those are the units for distance and time there. That's for the point of rate for us. So the units can sometimes help us out. Sometimes one of these formulas will be the better formula to work with, depending on what what the thing is given for you. But let's just go for it here. So we have a problem here. Amy and John leave Porterville at the same time towards Vegas. Amy drives twice as fast as John in 3 hours. She is 105 miles ahead of him. How fast are they driving? Okay. So usually when we do distance equals rate times time problems, I like to write it out, rate times time, and I like to create a table for this. We have John, and we have Amy. Okay, what's the distance they have gone? Huh. I don't think Amy and John, they definitely have a distance. We leave for Porterville and we're going to Vegas, right? Um, a little Vegas trip. I don't see anything that says the distance of each of them. So I'm just gonna kind of leave those as variables. I'll put a little sub j for the distance John goes and sub a for a distance Amy goes. Okay. How fast are they going? Are they going like 10 miles an hour, 100 miles per hour? Well, they don't give us that either, but they give us kind of a hint that however fast John is driving, Amy's driving twice as fast. How fast are they driving? Well, I can again set another variable for this, but there's a relationship between these two variables, right? If John is going an x speed, actually, I'll change this to if John is going an x speed here, Amy drives twice as fast. So how fast is Amy driving? Well, 2x. Distance is equal to times. And we're asking, oh, in 3 hours, she's 105 miles ahead or whatever, but they've both driven, it looks like 3 hours here. So 3, 3. Cool. So what do I have? I have two equations. Distance of John is equal to 3x, right? 3 times x, or x times 3. Distance of Amy is equal to 6x, where x is your speed. If I know my speed, then I know the distance of both of them. Now we're going to add one more piece of information. Amy has a distance of 105 miles ahead of him. How do I write that as an equation? I have Amy's distance is 105 miles more than John's distance. That is what that small sentence gave us another equation here. Well, now that we're here, man, I know what distance John is in terms of x. I know what distance Amy is in terms of x. I can just plug those in. Let's go 6x is equal to, here actually I'll be even fancier with my colors here. Let's make this green. And then I'll do, this is in green, right? That distance is 6x is equal to 105 plus the distance of John is 3x. And actually, this equation becomes quite simple for us. Now we just, subtract 3x from both sides. That becomes 3x is equal to 105 divided by 3. And this looks like x equals 35, right? I can do that one in my head here. Okay, I got x equals 35. What was x here? X was whose speed? John's speed. John's speed. So, John's speed equals 35 miles per hour, right? It looks like we were going, what? We were doing miles and we were doing hours as their units, so it's miles per hour for units. What about Amy's speed? Amy's speed is what? Sorry, guys, can hear my dog walking around. Amy's speed is, well, you can look at it. Okay, well, if x is 35, well, Amy drives twice as fast, or Amy's speed is 2x, double whatever this is, double 35, that is 70 miles per hour. And man, if John is driving 35 down a freeway, they are going way too slow. 70 miles per hour is like more of a standard speed for like going down a freeway or going to Vegas or something like that, right? Okay, let's do another distance equals rate times time problem. These ones are pretty tough here, right? A rowing team rowed, here, give me a second, let me get my doggo. All right, so now we have another distance equals rate times time problem. This is going to be your star problem as well. So I'll give a the case for when I'm going to do the star problem. Actually, wait, I'm gonna pause this video one more time. Okay, yeah, strap. This is not going to be the star problem. I'll have a star problem be like the next one or two. Okay, we have a rowing team that's rowed 60 miles while going with the current in the same amount of time as it took to row 10 miles going against the current. The rate of the current is 5 miles per hour. Find the rate of the rowing team in still water. So let's kind of like draw a little picture here, right? We have, some little ocean, right? We have going with the current, which means the water's kind of flowing that way. And we have a little boat, that they're rowing out. So they're going a certain amount of speed with the current. And then similarly, when they go against the current, right, they're going this way. It's kind of like the current is pulling them back, right? The current keeps pulling them back as they go forward. It's tougher to swim or row against the current, and it's easier to swim or row with the current. It works the same for wind, right? I think in uh in races, like in the like 100-meter dash or whatever, if the wind is going with you, it's easier to run. Whereas when the wind is going against you, it's worse, right? All right. So how do we do a problem like this? Well, I like to make the table. Distance equals rate times time. Distance equals rate times time, because this is one of those problems, right? We're doing a distance equals rate times time sort of thing here. Um, so here, like that. We have a rowing team. It's the same team, same people. So there's with the current, we're going a certain distance, a certain rate, a certain time, and against the current. All right. Well, rowing team, what's the distance we're going here? So the rowing team rowed 60 miles going with the current. So we're going to put 60 for with the current. And we went 10 miles against the current. So let's do 10 here. And it says it went the same amount of time as it took to row this. So whatever, we went 60 miles this way, and then we went 10 miles this way in the same amount of time. I don't know what that time is, but I know they're the same. So I'm just going to put T for both of them and make it be the same T, right? I don't know what it is, but that's good enough for me. The rate of the current is 5 miles per hour. Rate of the current is 5 miles per hour. So we have two rates, right? We have the current rate, which is 5, and then we also have the, I guess, rowing rate, because, these men are rowing on the boat. I don't know what that is, so let's put that as X, right? Well, with the current, we have both of these rates going together, which means I would add these two together. But if I'm going against the current, it means I'm rowing this way at a rate of X, and then I'm like slowed down by a rate of 5. So it'd be like I'm subtracting these currents, like so. Okay, so what equations does this give me? I have distance 60 is equal to rate times time. And then I have distance 10 is equal to rate times time here. Ah, So there's processes we've used for systems of equations with two unknowns, right? This is kind of like a system of equations. I'm going to use the substitution method, kind of like a version of the substitution method. I'm going to get t by itself on both of these problems here. To get t by itself in in the top equation, I'm going to divide by x plus 5 to get 60 over x plus 5 equals t. For the bottom equation, I'm going to divide by x minus 5, right? Divided by x minus 5, divided by x minus 5, right? I won't leave that there for the sake of the work. I'm going to have 10 divided by x minus 5, and the x minus 5 cancels on the other side. Okay, I have two equations. I want to combine them together somehow. Well, if time, is equal to this, and if time is equal to this, we can set both of these equal to each other because this is also equal to the same thing. These are equal to each other here. So combining these two, I have 60 over x plus 5 is equal to 10 over x minus 5. Now we've gotten our equation. We've done all that work to get the equation, and now we can do cross multiplying and work from there, right? I'm going to have 60 times x minus 5 is equal to 10 times x plus 5. I'm going to multiply this out, 60x minus 300 when you distribute, 10x plus 50 when you distribute. And now let's start canceling. I'm going to add the 300 to the other side at the same time, right? So these cancel, and I have 50x is equal to 350 or divided by 50, x is equal to 7. Find the, oh wait, what are we looking for? We're looking for the rate of the rowing team in still water. Well, when we started, the rowing rate was x. So I can say rowing rate in still water equals x. And we could call it a day from there. Cool, cool, cool. One more type of problem, as I know this will likely be a longer video, I apologize. One other type of problem are work problems. And the fun thing about these is they are similar to distance equals rate times time. There's just like another type of formula for how long does it take to go a distance. It's the same as how long does it take to do a certain amount of jobs. I'll say we also have jobs. The amount of jobs you do is the rate you are working times the time you do work, right? If I can write, you know, 3 essays a day, right? 3 essays a day, 3 essays a day, and I do this for 4 days, I've done 12 essays, 12 jobs, right? That's like the idea of it here. Um, and again, we like to abbreviate this for jobs is equal to rate times time. Or if you divide to get R by itself, I like to do R is equal to jobs per time, how many jobs we end up doing here. And usually it's like, how do we get the job done? The one job done. So I'll say this here, our problems only do one job done. I'm not trying to do 12 essays or 3 essays or something like that. Like, how long does it take me to do one essay? So in this updated formula, we have rate is equal to your one job and however long time it takes to do that job. Okay. And before we go to the full problem here, we have like another formula that I like to use for when we have like two people doing certain different rates, right? And this formula is involving combining rates here. So when you're combining rates, the idea in general is what is the rate of the first person times time. I'll do lowercase t for time here. Plus, what is the rate for the second person times time? And that together, if you're adding those two rates together, like the two people working together, that equals one job here. Sometimes if we're going to combine this formula with this formula, sometimes it tells you, oh, this person works for 30 minutes to finish a job. So I can say, for one job, this person takes 30 minutes. That's how you would do it. So to kind of update this, I would do rate one. For the first person, they can do one job, and I'll say T1 minutes times T. Plus the second person can do one job in T2 minutes for the second person's time it takes. And they're going for a certain amount of time. That equals one job. I'll even write this out. T1 equals first person's job time, how long it takes to do the first person to do the job. How long does it take the second person job time? Okay. So that's enough setup here. I might use one of these or the other of these formulas, depending on the context of the problem. So let's try this one. The Goomans, that's a fun name, need to mow their lawn before guests arrive. With their riding lawnmower, Sarah can mow the lawn in 30 minutes. I don't know why that's uppercase. Let's just put that as a lowercase. With a push lawnmower, like using your arms, right? Bobby, excuse me, can get the job done in an hour, 1 hour, or this is right, 60 minutes. How long will it take to work together? Well, let's try this. We have, what is Sarah's rate? Here. Sarah's rate, well, they can do one job in 30 minutes. 30 minutes. That is using this formula here, right? Bobby's rate is doing one job in 60 minutes, in an hour, right? So this becomes 1 over 30. This is one job in 60 minutes, or 1 in 60, right? In 1 minute, it takes a 60th of the job. In 1 minute, they get it done a 30th of the job. What if we combine those rates, right? You can kind of start doing this formula, but I'll just go to this one. I'll do this first one here. I have Sarah's rate times time plus Bobby's rate times time equals the one job done. You add the rates together for a certain amount of time. How long does it take to get the job done, right? So I'm going to go in this problem, 1 over 30 times t plus Bobby's rate is 1 over 60 times t is equal to 1. And 1 times t, I can just put that t in the numerator here. This makes life a little easier for us. Gypsies. And how do we solve for this? Well, this becomes an LCD problem. The LCD is 60. I can multiply everything by 60 here. And I'm left with, when I distribute 60 times t over 30, that becomes 2t. The 60s cancel on the second term, equals 60. 3t is equal to 60. 3t is equal to 60. Or t is equal to 20. Let's see if that makes sense, right? Sarah can get the job done in 30 minutes. Bobby can get the job done in an hour. So it took both of them longer to do it than working together. When they work together, it takes a faster amount of time. That makes sense because they are working together. Okay. Not bad. Okay, this one will have us our star problem. Star problem. Here. All right. What is the star problem here? It's another work problem. It takes a smaller hose twice as long to fill a certain swimming pool as it does a larger hose. So that's a big sentence. We have what we have. We have a swimming pool, right? And we have hoses. Let's do small hose here, and let's do large hose on like the other side. Maybe make this a little better. Let's go like that. Why not? I'm not an artist, as you can see. Small hose and large hose going into a pool, right? The small hose, if this was off, the small hose takes twice as long to fill a pool. And then the large hose will take twice as fast. If both hoses working together takes 35 minutes to fill the pool, how long will it take the larger hose to fill the pool? Well, I don't know any of these rates here, but if it takes twice as long for the smaller hose, let's say the smaller hose rate, let's say that is X here, right? I don't know what it is. But if it takes twice as long for the smaller hose to go, that means the larger hose rate is twice as fast. It takes twice as long for the smaller hose, so it's twice as fast for the larger hose. There you go. That works. So how do we do a problem like this? Well, if I have a smaller hose rate and a larger hose rate, let's use this one. I have rate 1 and I have rate 2. Let's plug that into that formula. I'll do rate 1 times time plus rate 2 times time equals 1 here. So rate 1 I know is x times time plus rate 2 I know is 2x times time is equal to 1. Um, don't we know what time is though? When they are working together to get the job done, to get that one job done, it takes 35 minutes. So I can update this again. X times 35 plus 2x times 35 equals 1 here. All right, now now we're cooking. 35x plus 70x equals 1 because 35 times 2 is 70. Adding these together, 105x equals 1. So when I divide, let's divide by 105, divide by 105. I have x is equal to 1 over 105. This is where these problems sometimes are not, these problems are not the greatest for finding the answer. Because what was x? X was a rate, right? X is rate of smaller hose. So when x is equal to 100 and 1 over 105, this is saying as a rate, right? Rate is how much one job and how much time. So this is one job in 105 minutes. The question is asking, how long will it take the larger hose to fill the pool? Well, I know how long it takes the smaller hose. The smaller hose, I'll say this here. Smaller hose takes 105 minutes. The smaller hose takes twice as long. So that means the larger hose will take half that amount of time. Larger hose takes 105 over 2 minutes, which this is 52.5. 52.5 minutes is the answer we were actually looking for. So, in these problems, it's kind of not enough to just be like, oh yeah, I got this answer or whatever. I found X, right? X in the way I set it up was the smaller hose rate. Um, I can use that to find how long it takes the larger hose to fill up the pool, but it just took a couple more jumps, a couple more leaps. So it's okay if this was tough. I would just say, keep thinking about it, keep working on it. So this is your star problem. I want you to write this stuff down, and I also want you to answer the question, what if um, the smaller hose takes, let's do 4 times as long. I don't want you to, so let's like say instead of twice, this is 4 times as long for the problem. I don't want you to like do the whole problem again. What I instead want you to do is get to maybe this point and do like a complete sentence, like get to like what this answer is and do a complete sentence on why the answer changed from this to like what your new answer is. So just do a full, just like a quick little, 1 or 2 sentence summary on what has changed in this setup here. Okay. This is going to be the last problem for this video. A swimming pool holds 4,800 liters of water. The pool has 2 drainage pipes. When the pool is completely full, the first pipe alone can empty in 240 minutes. The second pipe alone can empty it in 120 minutes. When both pipes are drained together, how long does it take them to empty the pool? Well, this is another work problem. Emptying the pool is the one job. So what are the rates of both of them? Pipe 1, I'll say pipe 1 rate and pipe 2 rate. Well, pipe 1 rate is what? The first pipe alone can empty in 240 minutes. So this first rate is, well, it can do one job. It can finish the job in 240 minutes. The second pipe alone can empty in 120. So it can do the one job in 120 minutes. Okay. Well, you can do, again, this formula here. You can view it as rate one or rate two. I'll go this one, like the rate one or rate two. I'm kind of liking that one a little better now that I'm looking at it. So let's go to rate one times time, or we'll leave it all in red, times time plus rate two. Oopsies. Rate two times time is equal to one job done. Let's add the rates together for that certain amount of time, and that equals the one job done. And there we go. So this becomes rate one. We can do the one job in 240 minutes for the first pipe. We can do the second job in, or the one job can take 120 minutes for the second pipe, and that equals one. And we're asking for how long it takes to drain or empty the pool. Well, we're asking for T here. So what am I going to do? Let's change this to T over 240 plus T over 120 equals 1. What's the LCD for a problem like this? What's the thing we multiply by to get rid of all the fractions, like in prior videos? It's 240. If I multiply everything by 240, what happens? When I distribute, I'm going to have just a T plus, when I distribute, 240 divided by 120 is 2T, or a 2, and then we have a T as well, is equal to 240. 3T is equal to 240 after combining like terms, and then we can divide by 3. Notice how like once I get to here, I'm kind of just like snapping through it, right? Because like once you feel more comfortable in these sorts of equation parts, you kind of just already know what to do for these problems here. And T equals 80 minutes. Does that make sense? We have one pipe that takes 240 minutes, one pipe that takes 120 minutes. We combine those pipes together, it should be faster work, right? If we're doing both together, it should be faster to do it. There we go. Okay, so that was a finished video. Again, probably one of the hardest videos of them all. So if you felt like you struggled, pause the video and, think about it. And please do the practice in ALEKS and use the explanation buttons on ALEKS for help as well. Thanks for watching, everyone.